This is a video showing how the calculation for the distance from the Earth to the Sun was arrived at by Edmund Halley, the famous English astronomer, in 1716. So he used the different speeds of the planets as they orbit the Sun to calculate the distance. This was a real key in the calculation. He also used parallax, Pythagoras' theorem, and trigonometry. So let's get straight into it. So here we go. So what was found is that as planets are closer to the Sun, they travel faster in their orbits. This was found by the famous astronomer Johannes Kepler. So Venus, because it's closer, travels faster than Earth, which is further away. So the further away you are, the slower you travel. So Jupiter, Mars, Jupiter, Saturn, etc., they'll travel much slower than Earth. And Venus, because it's closer, will travel faster. Mercury, which is closer again, will travel faster than Venus. So there was a pattern to the speeds. It wasn't just random or kind of disproportionate. There was a formula which seemed to govern the speeds, and it was found by Johannes Kepler. But first, let's just see what we really want here. So we want this distance, right? We don't know what this distance is, so let's just call it 1. Okay, so this is 1 astronomical unit, because we don't know what it is in kilometers, we don't know what it is in miles, so let's just call this 1 astronomical unit. So this distance from the Sun to Venus, well, at this point we don't know what that is either, and we don't know what size it is relative to the distance from the Earth to the Sun. So let's just call it XAU, okay? XAU. So then we go to, what do we know? What do we know? We know that Earth, the distance from Earth to the Sun is 1 astronomical unit, and the time that it takes for the Earth to go around the Sun, one orbit, is 1 year, 365.24 days for the Earth to go all the way around. So it's 1 astronomical unit and 1 year. I think we all know that. So how about for Venus? Well, we don't know the distance for Venus. That's going to be X. But do we know the time that it takes Venus to go around the Sun? Yeah, we do, because you can see this from Earth. It's not too difficult to measure, and it's 224 days. Venus takes 224 days to orbit the Sun. So let's put that information there. We know D is X. We don't know what it is, so we'll just call it X. And we know that time is 224 days, which is 0.613 Earth years, okay? So if you divide 224 by 365.24, you get 0.613 Earth years. So that's great. So where do we go from here? Well, Johannes Kepler, he found that the distance cubed is equal to the time squared. So the distance cubed measured in AU is equal to the time squared measured in years. So he found this. So D cubed is equal to T squared. So if we know the distance, if we know the time that it takes a planet to orbit the Sun, we can calculate its distance, which is very useful. So for example, let's do this for Venus quickly. So here we go. So for Venus, the distance is equal to X. So X cubed equals T squared, which is 0.613 squared, right? So that means X equals 0.613 to the power of 2/3. And if you go to your calculator really quickly, let's do this. So 0.613 0.7213 squared equals, and then cubed root, so 0.7216. But when you do it accurately, like with Excel, because it's not actually 0.613, the digits go further. So anyway, we'll find that x equals 0.7218 AU. So that's great. That's some useful information. So we find that D is equal to 0.7218 AU. And similarly here, 0.7218. So in other words, the distance, it's not apparent from this because it's not to scale, but so the distance from here to here is 72% of the distance from here to here. So if you wanted it to scale, it probably should be like out here somewhere. But anyway, so that's good. So relative to the Earth, relative to the Earth's distance to the Sun, Venus's distance is 72.18% of that. So that's quite useful. So that's all we can do from there. So if we move over to here, so this is just another way of showing that. So we have Venus travels around the Sun and Earth traveling around the Sun. Alright, so we have 2 points marked on our map here. So if you should know your geography, so this is obviously Africa. We have Cairo up here, capital of Egypt, and we have Durban in South Africa. So why do we have them marked? So let's find out. First, we're going to look at a quick video. So this is called the transit of Venus. So the transit of Venus is quite similar to the moon for an eclipse. So for an eclipse, you can see the moon gradually travels across the sky and coincides with the position of the sun and covers the sun. Now Venus is bigger than the moon, but it's much further away, so it appears pretty small. So Venus just does the same thing as the moon when it's in the eclipse. It just travels across the face of the sun. Again, it's further away, so it appears much smaller. It doesn't cover the sun like the moon. But this phenomenon is very useful in the calculation, and it's actually critical. So here we go. You'll see it just travel across, same as the moon, except it's much further away. It travels across the face of the sun. And there you go. So that's quite amazing, really, when you see it like that. So this is going to be key to our calculation. So here we go. So let's go back here. So let's jump over here. So what happened is this phenomenon, the transit of Venus, was viewed from Cairo. So they got an astronomer in Cairo or whatever, go to Cairo, and one in Durban. Actually, I'm not sure on the locations, but for this example, let's just imagine it. So they got an astronomer here and an astronomer down here. So they looked at the transit of Venus. So they viewed this phenomenon. They viewed this from these locations, one in Cairo and one in Durban. Okay? So let's see how that helps us. So let's come back here. Let's move in. So when it's viewed from here and here, we actually get parallax. So parallax, if you can imagine, you can put your finger in front of your face and just a few inches, few centimeters in front of your face, close one eye and look at your finger, and then close the other eye and look at your finger, and it appears to move compared to the background, right? So the same thing happens here. Imagine Venus is your finger. This is one eye in Cairo and one eye in Durban. So as you close one eye, Venus will appear to move just like your finger. Okay? So here we go. So this is the view from Durban. Okay, if you look at Venus, it'll appear as like a black dot on the sun, and then from Cairo, it'll appear as a black dot on the sun, but it'll appear down here. That's like one eye, that's like your other eye. So it's quite interesting. This can help us a lot. And again, over a period of a few hours, as the same with the moon, as the moon moves across the sun in the eclipse, Venus will appear to move across the sun just the same. So what we find is this. We'll have these paths. So this will be the point, let's call this the point of first contact. This is where Venus gradually just comes in, just as it did in the video. It's just starting to come in and moves across. Similarly, it comes in here and moves across. So what do we notice? Well, we notice for Durban, it will take Venus a much longer distance, and hence a much longer time to travel across the sun, because it's further up. And for for Cairo, it will take a much shorter distance, and hence a much shorter time. So that's actually quite interesting for us. So here we use trigonometry to help us out. So what do we actually know? Well, let's come up here first. So we have the Earth, right? So it takes the Earth 365 degrees to go all the way around the sun. We know that. Or 365 days, excuse me, to travel 360 degrees, right? It's one circle. So in one day, it will travel 0.986 degrees, right? So you divide this by this. So the Earth moves at 0.986 degrees per day. So every day the Earth moves by that much. And then after a year it does a full circle, right? Now for Venus, it takes 224 days to do 360 degrees. So in one day it does 1.607 degrees. So it's 1.607 degrees per day. So imagine the Earth moves at 0.986, so let's say to here, but Venus moves at 1.607, so Venus moves further in its orbit than Earth. So if you're looking at Earth, Venus will appear to move away from you because it's moving faster, right? So again, this is very useful for us. So here we go. So in the observations, so the speed difference, we'll just calculate the speed difference. So speed difference is 1.607 minus 0.986, which is 0.6215 degrees every day. So every day Venus will move 0.6215 degrees away, further along than Earth does. So that's how much faster Venus is than Earth in its orbit. So that's equal to, when you divide by 86,400, it's 0.0000719 degrees per second. So every second Venus moves this 7.19 by 10 to the minus 6 degrees further along its orbit than Earth. So again, that's very interesting. So when viewed from Cairo, it was found that it took Venus 16,250 seconds to travel from the point of first contact to the point of last contact, right? So 16,250 seconds. So we'll see that here from Durban, the view from Durban, it takes 25,000 seconds from the point of first contact to the point of last contact. But from Cairo, it only takes 16,250 seconds for it to travel across. So this is quite useful for us. What we also know is that when you measure the sun in the sky, so when you measure the angle, the size of the sun in the sky, it measures at 0.53 degrees, or whatever, 31.5 minutes, right? So 0.53 degrees is the size of the sun as it appears from Earth. So this is all very useful for us. So what we can say is this: if we come here halfway, move this to halfway roughly, and move this to roughly halfway. So what we do know is that that this is obviously well, let's just half this. This will be very useful for us. Yeah, there you go. So we've halved these, right? So to do half the sun, it takes 12,500 seconds up here, and to do half the sun down here, it is 8,125 seconds, right? So to get from the middle of the sun to the edge here is 12,500, and 8,125 down here, which is fair enough. Now we know the speed, right? The speed is 0.00000719 degrees per second, right? So if we multiply 12,500, right? If we multiply that by let's multiply that by 0.00000719, we will get the distance in angular measure for this. That turns out to be 0.08988 degrees. Oh, excuse me. So yeah, 0.08988 degrees. And similarly for down here, we have 8125 by the angular speed, so it's 0.00000719, which is 0.05842 degrees. So you can see this angular measure is larger than this one, which makes sense. So that's that in angular measure. So we see the size of that angle measured from Earth is a lot. It's like 60% bigger, which makes sense for us. So the next thing is this, the sun. So we can say the diameter is that size, but what about the radius? Well, the radius is going to be half that size, isn't it? So it's 15.75, 0.265. So that's the radius measure. It's half the diameter. So what do we also know? Well, we also know this, that this distance is a radius. So it's the same here as it is here. So that distance, same as that distance, same as that distance. So they're all the same. So what are we seeing here? What are we beginning to see? Well, we're starting to see triangles. So let's make some right angle triangles. So if we look here, this, so what we call this, let's call this H1, height 1. So H1, what is this height? Well, we have a triangle here, right? this one. And we have this side, and we have the length of this. Let's just get rid of this for a second. So we have this length of the hypotenuse. We have length of one of the sides in a right angle triangle. So let's just get H1, Pythagoras' theorem, which isn't too difficult. So I've got H1 squared plus 0.05842 squared equals the hypotenuse squared, 0.265 squared. When you do that on your calculator, H1 equals what? So let's do it quickly. So you got 0.265 squared minus 0.05842 squared square root. So what I get is 0.25848 degrees. Right? So that's what I get for H1. Now what about H2? So H2 is going to be this distance here. So, oops. So we know that this, sorry, H2 is here. So we know that this distance from here to here, we remember that? I think it was 0.08988 degrees. So we know that distance. Now we no longer need, we no longer need this. We no longer need this. Yeah, we can leave that there. So we have a triangle H2, this distance. We know that side. We know that side. So now we just need to get H2. So let's do it. So H2. Similar to Pythagoras' theorem. H2 squared plus 0.898, excuse me, 0.08988 squared equals 0.265 squared. So that means H2 equals, so 0.265 squared minus 0.08988 squared square root. I'm getting 0.24929. 0.24929 degrees. Alright, so now this is quite interesting. So what is H3? So H3 will be this distance from here to here. H3, well, it's pretty straightforward. So we can say H3 equals H1 minus H2, and that equals 0.25848 minus 0.24929. That equals, what does that equal? 0.25848 minus 0.24929. So I get 9.19 if I 10 to the minus 3. So it's 0.0091 H3 finally. So we know it's 0.00919 degrees. Okay, so that would mean that this here is 0.00919 degrees. Okay, so we cleaned up those calculations. So let's zoom out. So what we've got is we have this angle here now, and so now we can finally calculate the distance to the sun. You might not see it right now, but you'll see it in a moment. So we have this now, and what we also know is the distances from the sun to Venus and the sun to Earth in terms of AU. So we know, for example, that the distance from the sun to Venus is 0.7218 AU, and the distance from Venus to Earth, obviously this is 1, so this is 1 minus this, which is 0.72782 AU. We calculated that earlier, if you remember, here. So if this is 0.7218, this is what's left over, which is 0.2782 AU, right? So now we have some triangles here, which is quite interesting. So this angle basically is that angle there. So that angle there is 0.00918 or 919 degrees, which means that angle is also the same. What we find is actually this line, it isn't horizontal, right? So it looks horizontal, but actually it isn't. So what we should do here is actually divide this. We should split this in half. Right, we split this in half and we get a triangle here. So you can see from here to here. Sorry, that's a bit better. Right, so we have a triangle from here, here, up to here. So we take that triangle. So the angle in here is what? What is this angle? This angle here, let's call it theta. So theta equals 0.00919 degrees divided by 2. So that equals 0.004, it's roughly 46 degrees, right? So we can just draw that triangle roughly. It's like this. There we go. So we have this angle here, that's theta. This is, it's still the same, so 0.72782 AU, and this distance here, so actually the distance from Cairo to Durban is 6650 kilometers. So half that distance is 3325 kilometers. Okay, so this is 3325. Right, so let's do this. So 0.0046 degrees equals what? 10 opposite over adjacent, 3325 over 0.0046. 0.2782 AU. But for tan is inaccurate for very small angles. It's actually inaccurate, and especially in degrees it's quite small, so we should convert that to radians. So that equals tan. Let's convert. So to convert degrees to radians, you multiply by 2. I'll just do it quickly up here. So 0.0046 degrees by 2 pi over 360. That's how you convert degrees to radians. So it's 2 pi over 360 by 0.0046. So what I get is 8.0285 rads multiplied by 10 to the minus 5. So it's very small. So it's 8.0285. Excuse me. By 10 to the minus 5. Divided by 10 to the minus 5. That equals 3325 over 0.2782 AU. Right, so let's just zoom out for a moment. So that means this AU equals, what does AU equal? It equals 3325 over 0.2782 by 10 8.0285 by 10 to the minus 5. So I just rearranged this formula. Okay, so I brought this over here, I brought that down here. So let's do it out. So we got to make sure we're in radian mode. 10 of 0.00008 0285 multiplied by 0.2782 inverse by 3325. So AU, what we'll get is 148,867,574 kilometers. So how many miles is that? Divided by 1.609344. So it's 92.5 million miles. So that's our answer, and that's actually pretty close. So we're saying that it's equal to 148,867,574 kilometers. So we can check that online. So we can just go Earth to Sun distance. So Earth to Sun distance 149.6. Yeah, we're pretty close. We use surrounded figures, so, and it actually changes, it actually varies, as you'll see here. it varies throughout the year by 5 million kilometers, so we're right in that range, so we can say we're accurate. So yeah, that's how you calculate the distance of the sun from the Earth. I know it's pretty complicated, but we got there, and it all makes sense. So thanks for watching, and see ya.